Welcome to the IPv4 versus IPv6 module. By the end of this module, you should be able to describe the differences between IPv4 and IPv6. IPv6 is a next-generation protocol designed to eventually replace IPv4, which is used primarily in networks today. Defined by the IETF, IPv6 is seen as a redesign of the IPv4 framework, primarily due to the depletion of available IP addresses. There was an experimental protocol named Internet Stream Protocol, or ST, that was considered by some to be IPv5, but ST was never officially known as IPv5 and never passed experimental stages. Although address exhaustion was a major reason for the development of IPv6, several other issues exist that IPv6 attempts to resolve. The displayed table shows some of the differences between IPv4 and IPv6. Some of the additional benefits of IPv6 include more efficient routing, quality of service, or QoS, elimination of the NAT requirement, network layer security with end-to-end IPsec, ease of management using stateless address autoconfiguration, or SLAC, an improved header format to reduce header overhead. IPv6 headers include improvements over IPv4 headers that provide more efficient processing. Where IPv4 has a 40-byte field set aside for special options, IPv6 supports extension headers that can be appended to the IPv6 header to support additional options. The IPv6 header has a fixed length of 40 bytes and includes the following fields: version, which is a 4-bit field containing the number 6, which indicates IPv6. Traffic class, which is an 8-bit field that determines the traffic priority. Flow label, which is a 20-bit field used for QoS management. Payload length, which is a 16-bit field that indicates the size of the payload in octets. Next header, which is an 8-bit field that indicates the next encapsulated protocol. Hop limit, which is an 8-bit field that replaces the time to live, or TTL field, in IPv4. Source address, which is a 128-bit field, and destination address, which is a 128-bit field. IPv4 headers and IPv6 headers share several characteristics. For example, the version, source, and destination fields from IPv4 were carried over to IPv6. One of the biggest differences between an IPv4 packet and an IPv6 packet is that if IPv6 needs to fragment a packet, it uses extension headers to do so. Several fields from the IPv4 header were dropped in favor of a more streamlined, efficient header. Because the IPv6 header is always a fixed size, the header length is no longer necessary. If a packet requires fragmentation, extension headers will take over the process using the Path Maximum Transmission Unit, or Path MTU discovery. Some fields in the IPv6 header were moved from their previous locations in IPv4. The type of service, or TOS field, was replaced by the traffic class, or TC field. The TTL and protocol fields were also renamed and moved in IPv6. The flow label field is a new field in IPv6. As mentioned previously, the IPv6 header was improved with faster packet processing in mind. Because the IPv6 header has a fixed size of 40 bytes, the options that were once included inside the IPv4 header are now appended to the IPv6 packet using extension headers. 6 extension headers can be used in IPv6. They are hop-by-hop options, which signifies that the options need to be examined by each node along the path of a packet. Routing, which provides a list of intermediate nodes that should be visited on the path to the packet's destination. Fragment, which signals when a packet has been fragmented by the source. Destination options are the options examined only by the destination node and capable of appearing twice in a packet. Authentication header, which is used with IPsec to verify the authenticity of a packet, and encrypted security payload, which is used with IPsec and carries encrypted data for secure communication. Welcome to the IPv6 Address Types module. By the end of this module, you should be able to explain the IPv6 address format and the different address types. The escalating demand for IP addresses was the driving factor for IPv6. IPv4 uses a 32-bit address, supporting approximately 4.29 billion addresses. In comparison, IPv6 uses a 128-bit address supporting approximately 2 power 128 addresses. If 2 power 128 doesn't sound like a big number, think of the number of available addresses in another way. Enough IPv6 addresses exist to supply about 2 power 95 addresses for each person on Earth, or about 2 power 52 addresses for each observable star in the known universe. You should be familiar with the 3 types of IPv6 address that exist. The unicast address is a unique address that identifies an interface or a node. A packet with a unicast address travels only to the interface identified. A multicast address is an identifier for a group of IPv6 interfaces that might belong to different nodes. An IPv6 packet with the multicast address as the destination travels to all interfaces in the group. An anycast address is an identifier for a group of IPv6 interfaces that might belong to different nodes. However, unlike multicast addresses, an IPv6 packet with the anycast address as the destination travels to only one of the nodes identified in the group, typically the nearest node. At first glance, an IPv6 address can look alarmingly complicated. IPv6 presents a 128-bit address in 8 16-bit hexadecimal blocks separated by colons. However, IPv6 does provide for abbreviation. Consider these examples. You might think that you are looking at 3 different IP addresses, but in fact, you are looking at the same address in all 3 examples. 4 consecutive zeros in an address can be identified as a single zero. You can omit leading zeros from the notation. A double colon can replace consecutive zeros, leading zeros, or trailing zeros. However, you cannot use a double colon twice in an address notation. Doing so will result in the misinterpretation of the IP address. IPv6 has some similarities to IPv4 in text presentation. The prefix determines the network address or subnet. The example shows a 64-bit prefix. The prefix is noted. Just like with IPv4, certain prefixes are reserved and should be used for specific types of traffic. RFC 4291 defines the latest rules regarding prefix notation. A few examples are shown in the table. Similar to IPv4 nodes, IPv6 nodes must receive IP address assignments from their ISP. ISPs find information about their regional registries to verify if an IP address is in use. Address allocation is a work in progress, but RFC 3177 specifies a few rules that you should follow, which are represented in the table shown. The /16 prefix is reserved for special addressing. The unspecified address is similar to the default address in IPv4, and you should never assign it to an interface. The loopback address is a string of 127 binary zeros followed by a binary 1. It is denoted as /1. A host uses the loopback address to send an IPv6 packet to itself. The IPv6 loopback address is functionally similar to the IPv4 loopback address. Like the unspecified address, the loopback address is not directly assigned to an interface. IPv6 addresses have scope, which identifies the application suitable for the address. Unicast and multicast addresses support scoping. Unicast addresses support 2 types of scope, local scope and global scope. Link local unicast addresses are used within a single network link. The first 10 bits of the prefix identify the address as a link local address. Link local addresses cannot be used outside a network link. Multicast addresses support 16 different types of scope, including node, link, site, organization, and global scope. A 4-bit field in the prefix identifies the scope. The link local unicast address is identified with the binary prefix, 10 bits, followed by a string of 54 binary zeros, the host-generated interface ID, and a 64-bit mask. Any host can automatically generate this address on all of its IPv6 interfaces. Because the first 64 bits are the same for every link local address, this address is guaranteed to be unique only on an individual link and could be duplicated by hosts on other subnets. Link local addresses are never routable. Interfaces configured for IPv6 automatically generate a link local address. This address is often used for neighbor discovery, auto-configuration, and routing protocol traffic. Link local addresses were designed to provide automatic address configuration for small networks with a single subnet. Global unicast addresses are globally unique and are used to connect to and route through the Internet. These addresses are identified by the following different fields. Format prefix. The binary prefix 001 is present in the first 3 bits, as this identifies the aggregable global unicast address space. This is the only range currently assigned by Internet Assigned Numbers Authority, or IANA, for address allocation. Global routing prefix. The next 45 bits are reserved for hierarchical address allocation. These bits are used to provide the highest level of address summarization typically applied at Tier 1 ISPs, regional address allocation entities, or possibly large peering points. It is extremely important that these bits be allocated wisely, because they will have a large impact on how the Internet is routed. Subnet identifier. The next 16 bits are reserved for local assignment to a link. The local administrator uses the subnet identifier, or SID, to provide subnetting capability within a site. Interface identifier. The last 64 bits are reserved for the interface ID, permitting easy auto-configuration of a host on a network. The interface ID is a 64-bit field that uniquely identifies a host on a subnet. On Ethernet interfaces, it is a permutation of the MAC address associated with the interface to which the address is assigned. The interface ID is expressed in the IEEE Extended Unique Identifier 64 or EUI64 format. Because the host can determine the subnet to which it is connected by router advertisements and can generate its own interface ID, IPv6 addresses are easy to configure automatically on any host. Because Ethernet MAC addresses are only 48 bits long, the address needs additional bits to widen it to the specified 64-bit length. To obtain an Ethernet interface ID, concatenate the first 24 bits of the MAC address, company ID, with the binary value, and the remaining 24 bits of the MAC address, manufacturer extension ID. EUI64 addresses set the universal/local bit to a value of 1 to signify that this address is globally unique. The universal/local bit is the next to lowest significant bit of the first octet of the address. EUI64 addresses inverse the 7th binary bit from the left in the company ID. For example, take the 00:10:A4:A6:69:D0 MAC address. Here, the company ID is 00:10:A4, with the displayed binary equivalent. Note that the 7th binary bit is 0. When you inverse the 7th binary bit to 1, you get the displayed binary equivalent, whose hexadecimal value is 02:10:A4. When you append Ethernet interface ID and manufacturer extension ID to this company ID, you get the EUI64 address of 0210:A4FF::FEA6:69D0. Welcome to the IPv6 Autoconfiguration module. By the end of this module, you should be able to explain how IPv6 stateless and stateful autoconfigurations work. One of the great tasks of network management is assigning the many devices in your network an IP address. In IPv4, address assignment is managed using two different methods. The first method is to statically assign an IP address to each device. This method is efficient only if the network is small and you do not plan to change IP addresses frequently. The second method is to configure IP addresses automatically using the Dynamic Host Configuration Protocol, or DHCP. With DHCP, a device that requires an IP address contacts the DHCP server and automatically receives an IP address. Although DHCP is considered easier to manage than statically assigning an IP address to a node, you must configure and maintain the DHCP servers. Static IP address assignment and DHCP are considered stateful configuration methods. One of the enhancements to IPv6 is the implementation of stateless autoconfiguration. Stateless autoconfiguration enables IPv6 nodes to automatically assign an IPv6 address to a neighbor, effectively eliminating the need for static address assignment and DHCP. An administrator can still use stateful configuration methods if necessary. Stateless autoconfiguration consists of several elements. Extended Unique Identifier, or EUI. This 64-bit hexadecimal value is used to identify an interface. If you do not specify an EUI value explicitly, the security device auto-generates it from the MAC address of the IPv6 interface. Router advertisement message. An IPv6 router sends this message to on-link hosts periodically, or in response to a router solicitation or RS request from another host. Information in a router advertisement or RA message can include IPv6 prefixes from the router, maximum transmission unit or MTU messages, specific routes to the router, whether to perform IPv6 autoconfiguration, and a time period for how long an address should remain valid. Router solicitation message. The hosts send this message to discover the presence of properties of on-link routers. When an IPv6 router receives an RS request from a host, it responds by transmitting an RA message back to the host. An RA announces the existence of the router and provides the host with the information it needs to perform auto-configuration tasks. Prefix list. This table contains IPv6 prefixes. When entries are present in the list, the router includes the entries in the RAs the router sends to on-link hosts. Each time a host receives an RA, the host can use the prefixes to perform address auto-configuration. Neighbor discovery, or ND, is the process of tracking the reachability status for neighbors in a local link. Defined in RFC 2461, several enhancements were made to ND since IPv4. ND combines and improves upon Address Resolution Protocol, or ARP, and Internet Control Message Protocol, or ICMP router discovery, and redirects to detect whether neighbors are reachable. A device views a neighbor as reachable when the device receives recent confirmation that the neighbor received and processed IP traffic or neighbor solicitation or NS requests. Otherwise, the device interprets that the neighbor is unreachable. An IPv6 router with ND enabled can send ND information to downstream nodes. ND is optional on IPv6 devices. Consider the displayed example. The following steps must take place for address autoconfiguration to occur. 1. On startup, IPv6 hosts A and B generate link local addresses from their MAC addresses. 2. Each host broadcasts RS messages. Each message uses the host link local address as the source address for the RS packets. 3. The IPv6 router receives the RS messages. 4. The IPv6 router transmits confirming RA messages to the hosts. These messages contain a prefix list. 5. The hosts use the prefixes to perform autoconfiguration. If stateless autoconfiguration is not desired, an administrator can manually assign a static address to a node. DHCP is also available. In IPv6, DHCP is known as stateful DHCP v6, and RFC 3315 defines it. Several reasons exist to configure DHCP v6. For example, you might want to implement a specific IPv6 addressing scheme across your network. You might desire dynamic assignment of IP addresses to DNS servers. In some cases, you might require dynamic updates to your DNS servers. For security reasons, you might want to exclude the MAC address as part of the IPv6 address. Note that DHCP v6 and DHCP v4 are independent and require separate configurations. Two routers with a unique local IPv6 address assigned to their GE0/0/1.0 interface are displayed. Unique local addresses are similar to the concept of private addresses in IPv4. They are not expected to be routable on the global internet. Instead, they are routable inside a more limited area, such as a site or between a limited set of sites. In practice, applications can treat these addresses like global scoped addresses. Originally, IPv6 private addresses were defined as site local addresses using FECO:10, but were later deprecated on RFC 3879, deprecating site local addresses for concerns regarding their lack of uniqueness. The RFC provides details on the potential issues that result from this lack of uniqueness. Unique local addresses were specified later when the IETF community recognized the need to provide for private IPv6 addressing. The specifics are covered on RFC 4193, Unique Local IPv6 Unicast Addresses. These addresses have a high probability of global uniqueness. You use the show interface terse command to verify interface status. In this example, you can see the site local address defined previously, along with the unique local addresses that the configured interfaces generated and assigned. You use the show route table inet 6.0 command to verify the routing table contents. In the example output, the interface routes are added for both the site local addresses and unique local addresses. Initially, all data link layer addresses of any IPv6 neighbor are unknown. As shown here, you can use the ping utility not only to verify reachability, but also to learn the data link layer addresses of IPv6 neighbors. After the ping operation succeeds, R1's neighbor, R2, is listed along with its IPv6 and data link layer address information. A multicast address is an identifier for a group of nodes. Unlike with any cast addresses, when a packet travels to a multicast address, all members of the multicast group process the packet. While IPv4 has defined multicast, IPv6 has redefined and improved it. Broadcast packets are not routable, and every node on a subnet must process them. Multicast packets, on the other hand, are processed only by nodes of the multicast group. Multicast packets can also be forwarded over routers. In IPv6, ICMPv6 is used for multicast group management to optimize multicast traffic. This process is referred to as multicast listener discovery, or MLD. Multicast addresses are identified by the high-order byte FF, or 8 ones in binary notation. The following three types of multicast addresses exist, as defined in RFC 4291. Solicited node multicast addresses are for NS messages. All nodes multicast addresses are for RA messages, and all routers multicast addresses are for RS messages. The Anycast address is a new type of address in IPv6, and RFC 2526 defines it. You can assign an Anycast address to multiple interfaces in a group. Multiple nodes might respond with the same Anycast address, but the packet will travel only to one of the nodes. An Anycast packet travels to the nearest node based on the notion of distance determined by the routing protocols in use. Anycast addresses offer the potential for a number of important services. For example, you can use an Anycast address to enable nodes to access one of a collection of servers providing a well-known service, without manual configuration in each node of the list of servers. You can also use an Anycast address in a source route to force routing through a specific ISP, without limiting routing to a single specific router providing access to that ISP. Welcome to the IPv6 Routing module. By the end of this module, you should be able to configure and monitor IPv6 routing. The example shows a sample default static IPv6 route configuration. The operational mode command used for monitoring static routes in the INET 6.0 routing table is displayed. A sample OSPF v3 configuration for 2 neighboring routers is displayed. Note that OSPF v3, similar to OSPF v2, uses a 32-bit router ID or RID, which is defined under the Edit Routing Options hierarchy. Although you can dynamically select the RID from IPv4 addresses defined on the router, it is recommended that you always configure an RID. Most operational show commands used for monitoring OSPF v3 are nearly identical to the commands used for monitoring OSPF v2. The key difference is that you must replace the OSPF portion of those commands with OSPF 3. A number of common operational commands for both OSPF v2 and OSPF v3 are displayed for comparison. A sample ISIS configuration using IPv6 addressing instead of IPv4 addressing is shown. Note that other than the IP addresses, the ISIS configuration is the same for IPv6 and IPv4 environments. You can use the same operational show commands for ISIS in IPv4 and IPv6 environments. A sample BGP configuration is shown here. BGP configuration is almost identical for IPv6 as it is for IPv4. The major difference is that you specify an IPv6 address for the local and peer addresses rather than IPv4 addresses. You use the same operational show commands for BGP in IPv6 environments that you use in IPv4 environments. The show BGP summary command for 2 IPv6 peers in different BGP groups is shown here. Welcome to the use case, IPv6 over IPv4 tunnels module. By the end of this module, you should be able to implement IPv6 over IPv4 tunnels. The broad transition method suggests using tunnels to span IPv4 networks until all the intermediate routers have been upgraded to support IPv6. Tunneling requires encapsulation of the IPv6 packet within an IPv4 header. The new IPv4 packet is then forwarded across the IPv4 network to the other side, where the IPv4 header is removed and the IPv6 packet is either processed or forwarded. Many approaches to tunneling have been defined. The 4 approaches which are currently the most promising are IPv4 compatible addressing, configured tunnels, 6-to-4, and 6-over-4. The objective and topology used for the IPv6 over IPv4 tunneling, also known as configured tunnels use case, are displayed. The tunnel interface configuration for the R1 and R2 devices is shown. The displayed configuration shows the required routes for the R1 device. The IPv4 static route is used for establishing the GRE tunnel, and the IPv6 static route is used for directing traffic destined to the remote IPv6 network through the GRE tunnel. The output indicating R2's configuration is displayed. Although not shown in this example, all intermediary devices between the tunnel endpoints R1 and R2 in this example must have a route to the IP addresses used for the tunnel, typically loopback addresses. You can use the Show Interfaces terse command to quickly verify that the tunnel interface is up. Use the Show Route command to ensure that the required routes are installed. You should perform this verification step on both tunnel endpoints. The final verification task highlighted includes sending IPv6 traffic over the IPv4 base tunnel. Once IPv6 traffic is sent and received over the tunnel, you can use the Show Interfaces command to verify usage statistics on the GRE interface.